All right, today we are going to be going over the triangle inequalities. Let's get started. So, to start, we first need to define absolute value. Absolute value we're going to define as for all x in the real numbers. Absolute value of x is a piecewise function where it equals x if x is greater than or equal to 0, and it equals negative x if x is less than 0. So this gives us two cases. Case 1, x is greater than 0. So that means that the absolute value of x is just equal to x. And case 2 is going to be the absolute value of x is equal to negative x. That's when x is less than 0. Just negating both sides here, we get that the negative absolute value of x is equal to negative x. Oh, sorry, regular x. Putting these all together, we get that the negative absolute value of x is going to be less than or equal to x, and x is going to be less than or equal to the absolute value of x. You're going to hear me say the word absolute value about 300 times throughout this video, and that's for a very good reason, and that is that understanding absolute value is crucial in understanding the triangle inequalities. So let's do a little bit of practice. Let's think of some numbers. I'm going to think of -6, and we are going to just write this inequality out. So -6 is less than or equal to the absolute value of -6, and it's also greater than or equal to the negative absolute value of -6. This gives us -6, which is less than or equal to -6, and -6 is less than or equal to 6. This holds. We can try another number. Let's try 5. Oops, got ahead of myself there. 5 is going to be less than or equal to the absolute value of 5, and it's also going to be greater than or equal to the negative absolute value of 5. This gives us -5. This gives us 5. That holds as well. All right. Now that I feel like we all have a pretty decent understanding of absolute values, let's go on to the triangle inequality proof. Using what we learned above, let's consider two real numbers. We have x and y, they're real numbers. And so we know that that x is greater than or equal to the absolute value of the negative absolute value of x, and x is less than or equal to the absolute value of x. Similarly, negative absolute value of y is less than or equal to y, which is less than or equal to the absolute value of y. All right, so let's consider just x plus y, and we're going to get the following inequalities. We're going to focus on first the pink side, which is the left-hand side. So we get that the negative absolute value of x plus the negative absolute value of y is less than or equal to x plus y. And on the right-hand side, we have that x plus y is less than or equal to the absolute value of x plus the absolute value of y. Once we combine these, because they both share this lovely x plus y, things are going to start to look familiar, and you realize that x plus y is actually bounded by these inequalities. So over here, we have our left-hand side, and on the other side, we have our right-hand side. And let's sort of take a step back and think about what absolute value means. And it essentially is disregarding the sign of whatever number is inside the absolute value. And so using this sort of thinking, we can actually just sort of eliminate this side. Why? Well, because we know that that left-hand side is always going to be negative. Test that out. We just do like -3 and -2, and that gets us -3 and -2, which is -5. So it's just always going to be negative. and this side over here, always going to be positive. And using our definition from above, we can actually just slap some lovely absolute value bars on this x plus y. We're going to keep the right hand side, and we get that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. This right here is the triangle inequality. Yeah. So let's move on to the next inequality. This one's going to be the reverse triangle inequality. So we're going to start with the absolute value of x. Trivially, we know that the absolute value of x is equal to the absolute value of x. For our next step, we're going to do sort of a mathematician's favorite trick, which is we're going to add y, and then we're also going to take away y. So in reality, we're just sort of adding 0. We're going to come over here and remember the regular triangle inequality, which is, in its most abstract form, the absolute value of one number plus another number is always less than or equal to the absolute value of that first number plus the absolute value of that second number. And since the reals are closed under addition, I'm going to treat x plus y as one number, and I'm going to treat negative y as another number. So we have one number plus another number, which is perfect because they are both within these absolute values right here. So coming on down, we can pop both of these in some absolute values. And I'm not sure why these ones are blue. So we also have to change this equals sign over here to a less than or equals to. And things are starting to get a little spicy. Using a little arithmetic, we're going to move this on over. And also, this is a negative number inside an absolute value. So we actually don't care about that sign anymore. So we've got y, let's make this the same color, and we have here. So we've got the absolute value of x minus the absolute value of y is less than or equal to x, the absolute value of x plus y. And we're gonna stop our thinking here and move on to our next number, y. So once again, trivially, the absolute value of y is equal to the absolute value of y. And we're going to do that same lovely trick here where we add x and then we add negative x, effectively adding nothing. Then using the triangle inequality, once again, we are going to treat this section as one number and the negative x as another number. And doing that same arithmetic and getting rid of that sign, we get that the absolute value of y minus the absolute value of x is less than or equal to y plus x. Now, this isn't exactly what I want. I would prefer if everything was sort of in the same order, where you get x first and then y. So with this one, we can just sort of swap them. Addition is commutative, and with this y minus x, just do a little aside here, which is that the absolute value of y minus the absolute value of x is equal to negative the absolute value of x minus the absolute value of y. So I'm going to switch this over and we get this lovely, nice x first and then y section. All right, so what did we just do? Well, we now know that both negative the absolute value of x minus the absolute value of y and the absolute value of x minus the absolute value of y are both less than or equal to x plus y. If this looks a little familiar, you are right. We actually can create the following piecewise function, just like we did for the start of our definition of absolute value. So we get that the absolute value of x minus the absolute value of y told you I would be saying absolute value a lot, is going to be the absolute value of x minus the absolute value of y if the absolute value of x minus the absolute value of y is greater than 0. And we also have negative the absolute value of x minus the absolute value of y if the absolute value of x minus the absolute value of y is less than 0. If anyone is sort of wondering, well, why are we doing this piecewise function in the first place? This all really just comes back to we are assuring that this right here will always be positive. And we know we can do this because of the work we did up here, where we proved that both of these are going to be less than or equal to x plus y. So let's write our new inequality that we have, which is going to be the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x plus y. Whoa, this is the reverse triangle inequality. Some of you may be realizing that in both of these, we have the absolute value of x plus y. And this is a great thing to notice. So let's talk about it a little bit more. With our regular triangle inequality, we have regular, we know that x plus y is less than or equal to x, absolute value of x plus the absolute value of y. We also know that it is greater than or equal to I'm going to write it backwards here, the absolute value of x minus the absolute value of y. So actually this right here is the regular, and then this right here is the reverse. And this is honestly just a really cool thing to notice. You sort of see that what we're really doing here is creating an upper and a lower bound. So we have this lower bound of the reverse triangle inequality, and we have the upper bound of the regular triangle inequality. And they both sort of insulate our what everything is really all about, which is just the absolute value of x plus y. So now you've seen the reverse triangle inequality, and you've also seen the regular triangle inequality. But where are the triangles? You may ask, and that's where the geometric proof comes in. So a little history lesson on the triangle inequality, and it goes back to 300-ish BC, where Euler is sort of puzzled by the shortest path between 2 points. And in one of his postulates, he says that the shortest path is a straight line. Now, he doesn't prove this. He kind of just said it, which, I mean, it's true. It's true for Euclidean geometry. Maybe he knew, but one way to prove this is to sort of just consider a slightly different path where you go like this and you sort of form a little triangle. How do we know that sort of this side here and this side here added together are shorter than our hypotenuse here? Well, you can prove this geometrically. So imagine we have our triangle A, B, and C. And we're going to just choose this pink side of the triangle. Let's call it AB. And what we're going to do is add a length of AB onto a side that is just not the same side, right? So we're not just going to go off and add one right over here. We are going to add a length of AB right over here. And since I can't draw a triangle very well, I've already drawn it down here. So we now get triangle ABC, and we also have triangle ADB, and once more we have triangle DBC. So what do we now know about our newly constructed triangle? Well, what we do know is that side AB is congruent to side AD. This is just in our construction. We set this as one of the rules for making our new triangle. We also know that this line here, DC, is on the same line as this line over here. So this DC is essentially just an extension of AC. So another way to write line DC is to say that line DC is line BA plus line AC. All right. Now, let's use the, this is a triangle with two congruent sides. So it's an isosceles triangle. And using the isosceles triangle theorem, we can state that these two angles are congruent. Let's call them alpha. So we know that alpha 1 is congruent to alpha 2. And we also can see that we, in the construction of our larger triangle DBC, we have created a new angle, this guy, which we will call beta. And visually, you can just see beta is a larger angle than alpha. So let's just write that out. Alpha is less than beta. All right, well, what does this really tell us? Well, we then have to go to the law of sines. And the law of sines tells us that the corresponding side to an angle is proportional to the size of the angle. A better way to understand that is because angle alpha over here is less than angle beta, we know that the side associated with angle alpha, which is going to be AD here, is going to be less than the side associated with angle beta, which is going to be DC. So let's write this on out. We get that we get that AD is less than DC. This isn't that helpful until we realize what we wrote up here about DC, which was that DC is equal to, so let's just rewrite AD, which is less than BA plus AC. And this is true for all triangles. So how does this sort of relate a little bit to Euler and him trying to, him talking about the shortest distance between any 2 points? Well, how it relates is that we now know that given some third point, or sort of a third route to get from one point to another, we now can concretely say that this side A, this side B, and this side C, that side A plus side B is greater than side C, meaning that side C is the shortest path between these two. And just like that, we actually were able to get to triangles.